We'll do it again. Good evening. Good evening. Oh, there we go. Okay. Good afternoon. Maybe I should say it that way. All right, guys. Here's what I want you to do to start off, just to confirm that you remember what we did last week. Okay? I want to see if you can write the electron configuration notation for sulfide. 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 S-2 sulfide. Now, in order to do that, you have to remember what happens to sulfur to make sulfide. So see if you can figure out sulfide. If you ever wonder why I wear a Band-Aid on my thumb, I lost a nail and it's gross looking. And some people would be like grossed out by it, so I try to cover it up. Okay, sulfide. Have we got it? Sulfide has a charge of what? -2. How did it get the charge of -2? Give me general. How did it get the charge of -2? It did what? Gained 2 electrons. So now then, here's the question. It gained 2 electrons where? In the outer energy level, which is the what? Third energy level, and the what subshell? P subshell. So now, if you know that, you should be able to tell me the electron configuration notation for sulfide. What did you write? 1s2. Whoa, what? 1s2. 2p6. 3p6. Now, I lost some of you there. Who does this look like? Argon. It looks like argon. Guys, why would an ion want to look like argon? It's more stable. It's more stable. So it has gained electrons to look like a noble gas. Does that make sense? Does that make sense that it would do that and want to do that? All right? Then if you understand that, I want you to tell me who else will look like argon. Obviously, argon looks like argon. You've just said sulfide looks like argon. Tell me who else is going to look like argon. I heard somebody say chloride. Is that correct? Chloride will look like argon. Let's stay on this side. Who else will look like argon? Phosphide. Phosphide will look like argon. Now, some of you are not following, so let me explain. Phosphorus has how many valence electrons to begin with in its normal just phosphorus atom? 5. Where are 3 of them? What subshell? P, and where are the other 2? S. Does everybody get that? Okay. Some people don't, so let's go back. what is the valence shell? The outer energy level. What is the outer energy level for phosphorus? 3. Do you see how that's where we are? That's the third row, so we're in the third energy level. So we are in the third energy level, and the last thing you would write is 3s2, 3p3. Yes or no? So is 3 the outer energy level? Yes, 3 is the outer energy level. How many electrons are there? 5. 2 of them, that's where you say 3s2. Yes? And 3 are where you say 3p3. So does that make sense that there are 5 total? Okay? If there are 5, what's the goal? 8 total, meaning 3 more in P, yes? So what does it do? Gains 3 to look like argon. Does that make sense? And that's why it becomes -3. Who else looks like argon? So we know phosphide looks like argon, sulfide looks like argon, chloride looks like argon, argon looks like argon. Tell me who else looks like argon. Say it again. Aluminum will not look like argon. Who will aluminum ion look like? Neon. Good job. Because what does aluminum ion have a charge of? +3, meaning it has done what? Lost 3. And if it loses 3, it started with 13. If it loses 3, it now has how many? 10. Who has 10? Neon. Okay? So aluminum will look like neon. Who else will look like argon? Potassium and calcium ions. Look at potassium ion. What charge does it have when it becomes an ion? +1. So what happens? It loses 1 electron to look like argon. What does calcium do? Lose 2 electrons to look like argon. Does that make sense? Did you see that? Is that making sense? So this whole column becomes, and you can't see it, this whole column becomes an ion with what charge? +1. How do they become an ion with +1 charge? They lose 1 electron. Particularly, this electron is located in the S subshell, yes? All right, your question.
Why does it become like sulfide?
Because the nonmetal ions change their ending to "-ide". That's the rule. The metals keep their normal name unless they are a transition metal, and then they have a Roman numeral or that us or ic ending. That should be on one of the periodic tables you've labeled. Okay? But it's just a rule. What does this entire column have a charge of when it becomes an ion? +2. What does it lose in general? The 2 electrons out of what subshell? S subshell. Okay? This aluminum becomes a charge of what? +3. Now, for all of these metals, would a +3 charge be a logical charge? Yes, it would. For all of these, a +3 charge would be a logical charge. Now, I didn't say they all have a +3 charge, but it would be a logical charge to have. Now, the question is why? Because the P has 1 and the S has what? 2 electrons. Now, some of you are saying, yeah, but what about the D? Where is the D subshell in relation to the S and the P? Further inside, isn't it? Think about that for a minute. What do you say before you get to 3D? 4s. Where's 4 compared to 3? 4 is outer, 3 is inner. Guys, if you have a coat on, what do you have to do typically before you take your shirt off? Take your coat off. You take your coat off. That's your outer. Then you can take off an inner layer. Does that make sense? But you have to take the outer layer off first. So even though you write 3D, who's outer? 4s. Even though you write 4D, who's outer? 5s. Even though you write 5D, who's outer? 6s. Even though you write 4f, who's the outer? 6s. And 5f, who's the outer? 7s. Which means everybody in this area has how many valence electrons? How many? 2. 2. 2. You all just told me who's outer? 4s. Who's outer? 5s. Who's the outer? 6s. And so are these 6s too. That's the outer. Then you all of a sudden said there's 10 valence. 3D is not the outer energy level, is it? What's the outer energy level? 4s. How many valence electrons do these have? How many valence electrons? 2, 2, 2, 2, and 2. All of these, D and F, all have 2 valence electrons because the outer energy level is from the S subshell electrons because we go there. We go there before we come back down. Remember me doing this? We go out to 4s, then back down to 3D. Out to 5s, back down to 4D. Out to 6s before we come way back down to 4f. So the outer is going to be made up of an S subshell or an S and a P subshell. So let me go back. All of these have 1 valence electron and they get an ion charge of +1. All of these have 2 valence electrons and they get a charge of +2. Now these would have 2 valence electrons, so it appears that a logical charge would be what? +2. That's what it seems like a logical charge would be. However, we only said these have a fixed charge of +2, didn't we? So let's talk about these first. In order for zinc to become a +2 ion, which it becomes, what had to be lost? 2 electrons. Where did they get lost from? (4s). 2 electrons from 4s. Did you lose anything out of 3D? Not at all. Same thing with cadmium. Where do you lose the electrons to become +2? And mercury is different, so we're not going to go there because mercury can be Hg2 or Hg, but in general it's losing those 6s. Here's the question that you have. Yeah, but you said silver is always +1. Why is silver always +1? Guys, there are always exceptions. Different things happen, and there is an exception. It's +1. I'm not telling you everything that goes on in this system. Okay? I'm giving you the basics. This is 109. I'm giving you the basics, okay? I will come back to this area in a minute, though, and we're going to talk about logical charges. Let's keep going before we come back to this area, though. I said that a logical charge here for this column would be +3. For sure, aluminum is +3. And why does aluminum have a +3 charge? It loses 1 electron out of what subshell? P, and 2 electrons out of, so who does it look like? Neon. Gallium could also have a logical charge of +3 if it lost 1 electron out of P and 2 electrons out of S. Now some of you are wanting to say, but why doesn't it lose the ones out of D? Where is D compared to 4s? Inner. So you with me now on why it would lose the outer first? All right, let's keep going. This column we did not give a definite charge to because they have 4 valence electrons. And in fact, carbon and silicon love to share. They would prefer not to lose or gain, although they will, but they like to share. So we're not going to deal with that. Although tin and lead, we did talk about a set charge, tin 2 and lead 2, tin 4 and lead 4, and I'm going to come back to those in a minute. What does this column have a charge of when it becomes an ion? Why? Why is it -3? Because it's going to gain 3 to look like the next noble gas. And then here, -2, again, to look like the next noble gas. In this column, -1 to look like the next noble gas. Is that making sense? So what I've just done, and what you have hopefully just understood, is that now, instead of me saying, here's the ion sheet, memorize these, and then I went and I said, label this periodic table, +1, +2, yada, yada. Now there's understanding to why is it +1? Why is it +1? It lost 1 electron. Why did it lose that electron? Because it's in the outer energy level. Is that making sense why I went about all this, hopefully? Okay. Now then, if you truly understand, then you will also understand a couple more of these and why they have those oddball charges. So you have iron. Iron, if you have your ion sheet out, that would be a good thing to do. Get your ion sheet out if you have it with you today. Has everyone seen the sign-in sheet? Has anybody not had the sign-in sheet? So on your back side of your ion sheet, you have the transition metals that can have varying charges. I want to give you some general rules. Before I talk about those specifically, I want to give you some general rules, and I think this will help. These are the general rules on how electrons are lost, okay? So let me give you some general rules on how electrons are lost. Let me just block a little section off here. In general, electrons are lost from outer energy levels and unfilled subshells first. Electrons are lost from outer energy level, unfilled subshells first. Second, electrons are lost from filled outer energy levels. Then third, electrons are lost from inner energy levels unfilled subshells and or those subshells that are not half full. The first place you will lose electrons is outer energy levels, unfilled subshells. That's like taking your coat off first. That's where you lose them first. Then you can lose them from outer energy levels that have a full subshell. Once you get rid of all the outer, then you may come to the inner energy level and lose electrons. But if you're going to lose them from the inner energy level, it will pretty much always be from one that's unfilled, subshell, or a subshell that's not half-filled. Now, where does this half-filled scenario come from? Where does that come from? Do you remember me showing you P along X, P along Y, and P along Z? Do you remember us talking about that? In our brains, 3 is half of 6. Yes? Everybody agrees with that, hopefully. And in our brains, we're thinking it doesn't matter where those 3 electrons are out of the 6. It's 3 is half full, right? That's what we would think. But it matters where they are. If this is the P along the x-axis, and this is P along y, and this is P along z, the actual way these electrons fill up these positions, they actually put 1 electron in P along x, then they put 1 in P along y, then they put 1 in P along z. They don't actually put 2 in px first. Because think about electrons. Do they want to be in pairs if they don't have to be? Think about something. Do you want to share? If you had your choice, would you share a room or have your own room? Most of you would have your own room. Okay? So what's happening? The same thing that typically happens in a house or in a dorm room, whatever. You put, mom and dad have their bedroom, then first kid comes along. You put them in their own bedroom. Second kid comes along, you put them in their own bedroom. Third kid comes along, you put them in their own bedroom. Is that an exactly half full situation? Forget mom and dad. Just yes. Okay? What about the fourth electron comes along? That's when you have to pair them up. So did that disrupt the half full? Yes. So if anything's lost, which one's going to be lost first? That one that kept it from being half full. Now apply that same scenario to that D subshell. And the first one I want you to write, I want you to just write the complete electron configuration notation for iron. Now I had to do it up here at the top of the paper. Write the complete electron configuration notation for iron. Fe. Complete electron configuration notation for iron. You write it, the whole complete electron configuration notation for iron. Okay, we ready? What'd you write? 1s2.
2s2, 2p6, 3s2, 3p6, 4s2, 3p6.
Okay, good job. That is the complete electron configuration notation for iron. Now, you tell me, looking at your ion sheet, what are the 2 charges for iron? Say it again. +2 and +3. First, you tell me how do we get iron 2+? Here's the whole thing. Now tell me, how do you get iron with a 2+ charge? Loses 2 electrons. Who does it lose? 4s. So then what do you write? 1s2, 2s2, 2p6, 3s2, 3p6, 3d6. How can I do that? Because what's missing? You just lost it, didn't you? You took your coat off. Yes? You took your coat off. You lost 4s2. You now have a +2 charge. Is that a logical charge? Absolutely. Now, 3+ is also logical. Why is 3+ logical? Say it again. You got it exactly right. Whoever said it. It makes D half full. Look at D right now. How many are in D? 6. What is half full for D? 5. So if it loses these 2 and 1 out of D, that's a what charge? That's not rocket science. If it loses these 2 and 1, that means a total of 3 lost. What's its charge? +3. And then is D exactly half full? Yes. So what is iron 3+? Write it. You write it. Because D can hold how many? No, D. P can hold 6. We're talking about D. D can hold 10. Because you lose the outer energy level first. And it was full. You didn't have a choice of losing an outer energy level that was unfilled because your outer energy level was full. So go in the order that I gave you. You lose outer energy level with an unfilled subshell first. We didn't have one. Second, you would lose an outer energy level with a full subshell. We had that. So we lost those 2 first, which gave it a +2 charge. Then we had a +3 charge, had to come from losing those 2 in the outside first and 1 from the inside. And that was a benefit because it then made D exactly half full. And exactly half full is more stable than when it's not half full. Full is the most stable. Okay? So the whole thing now for iron 3+ is 1s2, 2p6, 3s2, 3p6, 3d5. Yes or no? Okay. By doing this, I'm hoping that the memorization has a meaning. Now, some of you, I know you could care less. You just give you a sheet, memorize them, just leave me alone. I'm just going to memorize it. I don't care. I hope you're not that way, but I know some of you are. The rest of you that have a little bit of spark of curiosity, just think, this is cool. I may not want to act like it, but really it is kind of neat that you can figure this out like this, okay? Because it is. It's neat that you can figure this out. And then it takes away the memorization stress. Because you can just go say, well, that's not a logical charge. Like, for instance, is it a logical charge for iron to have a +4 charge? No. No. But what about tin and lead? If you really understand this, then you're going to know what happens with tin and with lead. Write the entire electron configuration notation for tin. Write the entire electron configuration notation for tin. What'd you get? You got it or not? Don't have it yet? All right, finish it up. Not when you're doing ions. No. Guys, the question was, can you use noble gas configuration when you're doing ions? No. Because it gets too confusing on what's lost. So on 10, do the whole thing. I know it's long. Do the whole thing, though. Do the whole thing. So have you got it? Thank you. Okay, what do you have for 10? The whole thing. 1s2.
2s2, 2p6, 3s2, 3p6, 4s2, 3d10, 4p6, 5s2, 4d10, 5p2.
Okay, yes or no? Does everybody get that? Okay, what's the outer energy level? 5. How many valence electrons are there? It's not 2. 4. Guys, you just told me what's the outer energy level. 5. How many valence electrons are there? 4. 2 are in P and 2 are in S. So the outer energy level is the 5th energy level. Look at the columns. Tell me valence electrons. First column. 1. Keep going. 2. All the middle is how many? 2. Then starting with boron. How many valence electrons? 3. Keep going. Except helium is 2. Everybody with me now? So 10 has how many? 4 valence electrons. Okay. What are the logical charges for 10? +2 and it's a metal. So forgetting minuses. It's a metal. That means it always does what? Loses. It becomes positive. It always loses electrons. So what are the logical charges? +2 and +4. Yes or no? Tell me what gets lost to become +2. What energy level? That's the easy one. 5. What subshell to become +2? P. Why does it lose P first? Because it is unfilled. Yes? So it will lose these two first. So if you were to write only that, then what have you written? Sn +2. Follow me? If I said write the electron configuration notation for Sn +4, then you would write everything minus this one and minus this. So it would end in 3d10, 4p6, 4d10. Yes or no? Now, without looking at your ion sheet, look at the periodic table and tell me the logical charges for lead. +2 and +4. Do you see that? Do you see those? So guys, I have tried tonight to teach you 6 charges on the back of that ion sheet by just looking at logic of what you've already learned. And then if you always remember the S's are lower than the X, you really have learned the old names and the new names. Because the logical charges for iron were +2 and +3. So that's iron 2 and iron 3. That's the easy one. Please don't make that hard. Iron 2 is plus 2. Iron 3 is plus 3. And that would be called ferrous and ferric. Yes? And then I've also taught you now tin 2 is plus 2. And it would be called stannous. Tin 4 is stannic. Yes, and it's plus 4. And then lead 2 is plumbous, and lead 4 is plumbic. So there's 6 from that whole back side, and those I think are the ones. The only one I didn't talk about that has that us and the ick is copper. And then chromic, the only one I have asked you to learn is chromic, and it's plus 3. So that should lower your memorization just by understanding it. And once you can understand something, man, to me that makes it so much easier. I think that's why, honestly, we probably all have so much trouble with people. We don't understand them. I mean, if we understood people, doesn't it make it easier? If you can understand why somebody does what they do, then you're like, oh, I understand why they act that way because they had da-da-da-da-da. But when you can't understand them, you just want to kill them sometimes because you don't understand them. And that's the same thing with this. What's your question?
I'm sorry, this just isn't clicking for me. How do you know the logical charges for lead?
Because lead is right underneath tin. What are the logical charges for tin? Plus 2 and plus 4. You lose these 2, and that makes it plus 2. You lose these 2 and these 2, and that makes it plus 4. If you wrote out the electron configuration notation for lead, you would see exactly the same thing, except it goes farther. And instead of ending in 5s2, 4d10, 5p2, it ends in, say it with me. You say it too, Sophia. 6s2, 4f14, 5d10, 6p2. So 6p2 is corresponding to this same thing here. It will get lost first because it's outer, unfilled. And then the 4f and the 5d you don't worry about because they're inside. So then you would lose the 6s2, and that would make it plus 4. Okay? Sit down and look at this and really focus on some logical charges, and I think it will make sense. I think it will start to click, hopefully. All right, let's leave this and let's get into some trends, and then we are going to talk about Lewis structures tonight. A little bit on nomenclature and then Lewis structures. So there are 3 different trends that we want to talk about. The first one is atomic radius. And atomic radius, I could have called it atomic diameter. You follow me? You have seen me stand up here and do this now for over a week, I think. When I do this, what am I talking about? The electrons in the electron cloud, but now we don't just say electron cloud, we call these what? Energy levels. Guys, if I have 7 energy levels, am I big or little? Big. Look at me. Big. If I only have 2 energy levels, I'm okay. You've just answered and basically said this trend yourself. You've answered the question of why the trend is what it is, and you've answered the question of what is the trend. So atomic radius means how big am I? What's my diameter as an atom? So here's the trend. Atomic radius increases from top to bottom within a group due to increases from top to bottom within a group due to, now go ahead and answer it, due to what? Increase in energy levels, the addition of energy levels. Due to the addition of energy levels. So it increases from top to bottom within a group due to the addition of energy levels. Atomic radius decreases from left to right across a period due to, and I'm going to stop there for a minute. First of all, would you expect all of the third energy level? In other words, would you expect sodium, magnesium, aluminum, silicon, phosphorus, sulfur, chlorine, and argon to all be about the same size? You would. I mean, I would. I would expect them all to be about the same size. Okay. We're going to try this. I'm not sure that these chairs are the best, but we're going to try this. I need a male helper. And since that's so limited, somebody just jump up and say, "Pick me, pick me." Have to call you out. Come on, you've been asleep. You need to wake up. You're who I wanted to pick anyway because you've been sleeping. Now, I'll sit in the bad chair because this one's going to fall apart. Maybe not, but have a seat. All right, so we would think that atoms in the same period would be the same size, yes? But I've just told you what do. They get smaller, okay? So he's going to be the protons. I'm going to be the electrons, all right? Scoot that way just a tad. There we go. Give me your arm. Hold on a minute. Okay? All right, so here's what happens. He's the protons. I'm the electrons. Who are we to start with? We're in the third energy level, so who are we to start with? So he has a power of what? If he's sodium, he has how many protons? Plus 11, and I'm representing what? Negative 11, but 1 in the outer energy level. With me? Okay? Then who do we become? Okay? Then who do we become? What's happening? Keep going, keep going, keep going. What's happening? We're getting closer together. Why are we getting closer together? What's adding on here? What's adding here? Protons. What's adding here? Electrons. What do opposites do? Ah. Did we attract to each other? Thank you. Do you see what happens? You would think they'd all be about the same size, but what's happening? The positive pull has more negatives to pull on, and so and they're not far, I mean, they are in their outer energy level, but what happens? That more attractive force gets greater and greater, and so what does the atom actually do? It starts to shrink. It actually decreases in size. And so what you can say is decreases from left to right across a period due to the greater attraction between the additional protons and electrons. The greater attraction between the additional protons and electrons. All right, that is our first trend. We have 3 trends. That's our first of the 3. Every one of the trends all have something to do with atomic radius. So what we're going to do is we're going to look at these trends based on their relationship with atomic radius, meaning based on the atom size, because they all have something to do with it. First, you've got to get in your head, and I think this is where you were kind of off in my little show here. Positives and negatives do what? Attract. Okay. Positive and negatives attract. You got to get that in your head. So first, though, what is ionization energy? Before I even tell you the trend, you got to know what it is. Ionization energy is the amount of energy required to remove an electron. The amount of energy required to remove an electron. Now, I want you to think about what you already know and what you've seen me do. You've seen me now for over a week be just goofy up here in a sense. If this atom is like this, first, and I didn't ask this earlier, who's the biggest atom on the periodic table? Look at your trend. What's your trend? Read your trend. Increase from top to bottom within a group, decreases from left to right. Let me show you a picture. Maybe this will help you figure it out. This is a picture of atomic radius. Small, big. If that's the periodic table, relatively like a square or rectangle, who's the biggest atom on the periodic table? Francium. Why is francium the biggest atom on the periodic table? Because it has 7 energy levels, and how many electrons are in its outer energy level? 1. Is it highly attracted to its nucleus? No. But then as you go across, if you had more elements across that period, you would find they'd get smaller, just like it happens in cesium and radon. Radon is smaller than cesium. Cesium is bigger, radon smaller. Francium is bigger than cesium, though. So this is a picture of francium, okay? This is francium. You with me? I mean, isn't that just a funny thing? You know, I'm like, it's just huge. It's this huge atom, okay? You tell me this electron out here, this 1 valence electron out here, this 1 valence electron, is it easier to lose this one? Or is it easy to lose hydrogen's 1 valence electron? Which one's easier to lose? Francium's. They're both outer. Hydrogen only has 1 and it's outer, but this is its outer. This is francium's outer. Who will lose an electron more easily? Because it is bigger. Guys, when you carry something, you want to, I was watching or looking at myself, and I've done this more than once today. I carry my water bottle like this. I carry my water from the car lots of times like this. Do I want to drop it? It's glass. No, I have before. I don't want to drop it. If I wanted it to be easily removed, how would I carry it? Out like this. Where do we hold things we want to keep close to us and keep on us? Close to the nucleus. If it's farther from the nucleus, it's more easily taken. Guys, I think I said this last week. You're far from the nucleus. Some of you are right now. Some of you are doing things you would never, ever do at home. because you're far from the nucleus, and you're going to be taken if you keep it up. Just saying. Not wise. Okay? Get a little closer to the nucleus. All right? Find the nucleus if you need to find one to get close to, so that you don't do something you'll regret. So can we say that the trend for ionization energy is the same as atomic radius or opposite? The amount of energy required to lose an electron, will that decrease as you go down a family or increase? Atomic radius got bigger. Will ionization energy get bigger or smaller as you go down a family? So what is it in comparison to atomic radius? Opposite. So ionization energy is opposite. The trend is opposite trend to atomic radius. It is an opposite trend to atomic radius. Make another note to yourself. The smallest atoms require the most energy to remove an electron. Largest atoms require the least. Those small atoms, the smaller atoms, are holding on to their outer energy level electrons more tightly. The smaller atoms are. So they're holding on to them more tightly. The larger ones simply can't. The distance between their positive nucleus and their electrons is too far away. They can't hold on to them as tightly. That's why, because they're so big. If you wanted to draw a little picture, you would simply just draw the opposite of what we did. So IE stands for ionization energy, big, small. Big, small. Now, somebody out there is thinking ahead and they're wanting to say, so I'm going to say it for you, but I thought you said the nonmetals don't even want to lose electrons. They want to gain. They become negative. Is that correct? Is that a correct statement? Yes, the nonmetals want to gain. They don't want to lose. So what this is saying is a confirmation of that. In order for, let's say, fluorine to lose any electrons, is it going to take a tremendous amount of energy? Yes, it would take a tremendous amount of energy. Why? Because fluorine is very small, and it doesn't want to lose. It wants to do what? Gain. So it's almost like paying for it. If you want to take an electron from fluorine, you are really going to have to pay for it with a lot of energy to get rid of that electron. All right, electronegativity is the last trend we want to talk about. Let's write the definition for electronegativity, and then we'll look at the trend, okay? The definition is the attractive force for shared electrons in a molecule or polyatomic ion. It is the attractive force for shared electrons in a molecule or polyatomic ion. Wake up. The attractive force for shared electrons in a molecule or polyatomic ion. First, let's talk about polyatomic ions. The majority of the polyatomic ions are made up of what kind of element? Well, they have oxygen in them and another what? Non-metal. Think of your polyatomic ions. They're like nitrate, phosphate, sulfate, carbonate, chlorate, iodate. You with me? They're non-metals. What do non-metals bonded with non-metals do? Do they transfer electrons or do they share? They share. So why is polyatomic ion listed here in this scenario? Because they're sharing electrons. The atoms that make up polyatomic ions are sharing electrons just like in a molecular compound. We are talking now about sharing electrons. We're not talking about losing. This was losing electrons. We're talking sharing right now. So it's the attractive force for shared electrons in a molecule or polyatomic ion. We could also say how tightly an atom holds on to shared electrons. That's what electronegativity is. How tightly an atom holds on to shared electrons. Our problem is that we have this word share in our vocabulary. And my brain says perfect sharing, this is perfect sharing. I'm going to give you this for 5 minutes, and you get to hold it for 5 minutes, and I get to hold it for 5 minutes, okay? And we're going to share all day long, every day. We're going to share this pen. Now, is that perfect? How many of you know of any kind of sharing relationship that's like that? None. I know of none. Because honestly, that's what I feel like the word share means. In its perfectness, it's perfect sharing. But nothing that I can think of do we share equally. Typically, it's, I'm going to share this pen with you. Oh, no, I'm going to share this periodic table with you, and I'll let you have it back when I'm done. And she never gets it back. She shared it with me, and I kept it, right? That's kind of our world of sharing. Well, what we're dealing with here is, who is the taker? Who's the one who says, this is my periodic table and I'm going to hold on to it more tightly than you are? It's whoever's the most electronegative. Now, what did I say before we started talking about all of these? Every one of them have to do something with what? The atomic radius. Now, you tell me, who will have the greater attractive force for shared electrons? Size-wise, the smaller atom. Do you see that? The smaller atom. Guys, think about it. If this is another atom, and so in the middle here is the nucleus, this is the outer energy level of this particular atom. You with me? If I'm that big fat atom again, these are my outer energy level electrons. That's the outer energy level electrons for that atom. Here's my nucleus. There's their nucleus. Who is going to share and pull my outer energy level electron more tightly, me or them? Them. Why? Because their nucleus is closer to my negative electron. What's their nucleus's charge? Positive. What's my electron? What do opposites do? So my electron is going to be shared over there with them, and I'm not going to get to hold on to it as often, am I? Because I can't. Can I hold on to those shared electrons as tightly as that atom can? No, I'm too big. It's too far away from my nucleus. So the trend for electronegativity is what? The attractive force for shared electrons in a molecule. Largest atoms will have the what? lowest attractive force for shared electrons. So is this trend the same as ionization energy? Smaller atoms will have the what? Greatest attraction for shared electrons. So it's exactly the same. Same trend. Now, I'm not saying it's the same trend. So it is the same trend as ionization energy. Large atoms, what? Low what? Low attraction. Large atoms, low attraction, meaning low electronegativity. And small atoms, high attraction or electronegativity. So you could draw exactly the same trend chart. But the beauty of it all is, look at your periodic table. Look at the legend at the top of your periodic table. What do you see? Electronegativity. It's all there. For every atom on the entire periodic table, it's right here on your periodic table. What's the electronegative value or electronegativity value for fluorine? 3.98. Do you see that on your periodic table? Are you always going to have this periodic table for your test? Who is the most electronegative atom value that's shown? It is fluorine. Guys, is fluorine small? Yes. Is fluorine almost full with an octet? That means if fluorine shares with anybody, is it going to be pulling those other electrons to it more tightly than anybody else is going to pull its electrons? Does that make sense? That's what electronegativity is. Last scenario, and then I'll let this go and we're going to move on to Lewis structures. Up until this point, we have spent a lot of time talking about ions. We're going to today show sharing electrons, but I'm just going to show you a picture of this right now to start with, to get us in that mode of sharing electrons, and then helping you understand this electronegativity scenario. Right now, what I'm showing you is I'm being water, okay? So this is who out here. I've got two of them. Hydrogen. So this is hydrogen. Hydrogen has how many valence electrons? One. So just pretend this is my break at my elbow. So this is hydrogen's one electron. This is oxygen. Over here's another hydrogen. And here's its one valence electron. You with me? How many valence electrons does oxygen have? 6, okay? So go back. This is oxygen. There's 1, 2, 1, 2. Pretend you're seeing 2 dots up here, 2 dots down here, 1 and 1. Let's count that again. 1, 2, 3. Okay, we follow now? So by having this electron bonded with this electron from hydrogen, I have made a single bond. Are we sharing these electrons between hydrogen and oxygen? Same thing over here. Everybody with me? Now my question is, sharing is not perfect. Who has the greater electronegativity? Oxygen. Oxygen. Who holds on to these shared electrons more often? Oxygen. Now, this, in a sense, goes against some of the other things we've already said, though. We said the smaller atom would have the greater electronegativity. Hydrogen's smaller than oxygen. So why doesn't, and really it's kind of a toss-up on who would be smaller, hydrogen or oxygen. You think probably hydrogen would be smaller. But why does oxygen have the greater electronegativity? Well, first of all, here's the whole deal. Can hydrogen share more than 2 electrons? No. Hydrogen only needs 2, doesn't it? So who has the most electrons in this picture? Oxygen. Whoever has the most electrons in that scenario is going to be the one pulling the others to it more often because it's more negative. Is that making sense at all? All right, we're going to see more of this. We're going to see a lot more of this. So we're going to just start tying all this together, and I'm going to do something that's not a healthy thing to do. I'm going to assume something that I ended up having to figure out in my first class this morning. I found out that the majority of, well, I will not say that way. I found out that probably a fourth to a third of the students in my 8 o'clock class had not watched the nomenclature videos. I'll be nice to you. After they were quiet for most of the period, I asked them. I finally just said, how many of you have not watched the nomenclature videos? And it was about a fourth to a third if they were honest. I'm not going to ask you the same question, but here's what I'm going to tell you. I'm going to just give you a quick little snip of nomenclature, and then I'm going to insist you watch the nomenclature videos before Wednesday. I'm going to keep going on Lewis structures, and we will come back on Wednesday, and this is what you need to have with you on Wednesday if you don't have it today. These 2 papers, it's actually day 4 nomenclature notes. Do the video for day 4 nomenclature. Watch it. It's on acids. Watch it. If you haven't already, watch all 4 before Wednesday. Watch the nomenclature video on acids and do this sheet. Also, this is the back side of that, and it has all types of nomenclature. This is just day 4. That's what this is. If you print it out day 4, you have it already. If you have it filled out, which I hope you do, that's what you were supposed to have done before you came to class today, wonderful job. If you don't, go fill it out. But then bring this to class on Wednesday. Because on Wednesday, my practice with you over nomenclature is going to be answering any questions that you have over this sheet and doing some of these with you and kind of tying up any nomenclature loose ends. I am not going to give my whole lecture. The reason I say for sure also bring the acids is because this is where people tend to struggle more than anything. They tend to struggle with the acids, and then when we put it all together, and that's why I wanted to work on these for sure. We may work on other things, so if you bring it all, that's fine. But please watch those, okay? Please watch those. Do not think that I'm going to re-lecture all that nomenclature lecture in class. I'm not. I'm not going to do it, so make sure you watch it ahead of time. With that said, I want to go to the next page, which is a very quick little scenario of compounds. So let's look at just a real quick scenario of compounds. And this sheet shows us 2 types of compounds. And it's basically kind of what I call this is the quick notes. I call this the little quick notes sheet for nomenclature. The goal for each is the same, and that is an octet. What is an octet? 8. 8. And specifically 8 what? Who are we talking about? 8 what? Electrons. Okay. So the goal is an octet. Now, how do these atoms achieve their goal? There's 2 different ways they achieve the goal of an octet. If it's an ionic compound, what does it do to achieve that octet? Ionic. We've talked a lot tonight about ions. It loses electrons or it gains electrons to get to that noble gas look, right? Or close to the noble gas look. That's what's happening in an ionic compound. It's transferring electrons. It's a loss and a gain. But in a molecular compound, or covalent, as it's also called, what are they doing? Sharing electrons to make that octet. Now, I don't know if you caught on to my little water pitcher up here, but 2 was how many each hydrogen had, and that was right because they don't need an octet. But did you pay attention to how many now were around oxygen? These two, that's 4, 5, 6, 8. So are 8 around oxygen? Yes. So it achieved the octet by sharing electrons. That's what we were doing. So covalent molecules share electrons, ionic compounds transfer electrons. That is the huge difference. Huge difference, but the goal is an octet both ways. Usually, ionic compounds contain a metal. Now, there is an exception to this. Who are the only 2 exceptions that will not be metals? Ammonium and hydronium. So, usually metal or NH4 plus 1 or H3O plus 1. Ammonium or hydronium. Usually a metal plus a nonmetal, but this nonmetal could also be what? A polyatomic anion, meaning nitrate, sulfate, any of those negative polyatomic ions. We already talked about they transfer electrons. We can also say in a more specific way, rather than me putting this and then all the exceptions, they contain what? Cations, which are positive, and anions, which are negative. Which means we have to, notice what I'm doing, there was a typo there. We have to balance charges. So the positive equals the negative. We balance the charges so the positive equals the negative. And a lot of today we've spent talking about what these 2 things say. Metals do what? Form cations due to loss of electrons. Nonmetals do what? Form anions due to gain of electrons. And the last little snippet is no prefixes. You do not use prefixes in ionic compounds unless they're used in the name, like dichromate, for instance. That's the name of dichromate. But other than that, you do not use prefixes. In comparison, molecular compounds or covalent compounds are only what? Nonmetals. Straight up, only nonmetals, period. No exceptions. Only nonmetals. We share electrons. And since we share electrons, are we making ions? No. So there are no ions. So there's no charges, which means what? No balancing. Instead, use prefixes to indicate the number of atoms. And all that's on the video. I'm not going to write all the prefixes down. All that's on the video. But this is kind of like the short and the sweet of nomenclature. The difference between the 2 types. That's what this is. I'm going to let you do this before Wednesday. Watch those videos. Do nomenclature. Guys, there are lots of practice problems on Blackboard, blank worksheets. Print them out, do them, print them out, do them, print them out, do them. You cannot watch the video once and say, oh, yeah, I got that, unless you had a really good high school. You might have, and that's great if you did. But this is where students lots of times will falter, is on this material, because they don't learn their ions. They think it's not important. I don't care if I know this or not. I'm never going to have to know it. Well, then that second test, grades are down because they don't take it seriously. So you've got every avenue to learn it, but you've got to take the effort, okay? So let's move on. I'll come back here on Wednesday, but we're going to move on right now. We're going to talk about diatomic elements. Diatomic, what do you think that means? Two what? Di means two, two atoms. Two atomed elements, and that's what diatomic elements are. Elements that do not exist alone in nature. Elements that do not exist alone in nature. They are two-atomed elements. They do not exist alone in nature. They are two-atomed elements. They will be in a diatomic state or with another element. They will be in a diatomic state or with another element. Who are they? Who are the diatomic elements? Anybody know? Iodine is one of them. Good. Who said that? Good for you. Who are the diatomic elements? Hofbrinkel. You need to tell your teacher you remembered that. Hofbrinkel. Some people call it Brinkelhoff. Have you heard Brinkelhoff before? There you go. That's what he's talking about. That's it. Now, if you can't remember Hofbrinkel, which personally I don't see why you can't remember Hofbrinkel, but I'm going to give you two other ways to know who the diatomic elements are. You can remember Hofbrinkel. Now, some of you are like, what's Hofbrinkel? Let's go back there for a minute. Who is this? Okay. So those are the diatomic elements, but if you can't remember that, remember that there are 7 diatomic elements that start at number 7 and make A7 plus hydrogen. So go to your periodic table. Who is 7? Nitrogen. Now make a 7 starting with nitrogen. What do? Nitrogen, oxygen, fluorine, chlorine, bromine, iodine. Did I just make the 7? And who's the 7th one? Hydrogen. Does that make sense? Now you can't see hydrogen, but I colored it red over there too. Hofbrinkel, 7. Can't make it any clearer, okay? Remember Hofbrinkel. And the good thing is you actually already knew all this before you came to class today, because most of you, not all, but many, are wanting to be nurses. And so you have studied a little bit about nursing, or at least you've seen a TV show or been to the hospital or been to the doctor's office, and they said something about the person is not breathing well, give them some, they say give them some oxygen. But if they don't say the word oxygen, what do they say? Oh, what do they say? O2? Why would they say that? It's a diatomic element. Ah, that's why they say O2. Guys, you can't give them some O. Why can't you give them any O? O does not exist as O. You can't go get some O. As soon as you try to go get O, it's O2. As soon as O separates from O, it finds another O and it slaps together again. It can't exist alone. The funniest scenario to think of this is girls who cannot be by themselves. You ever met a girl who had to go to the bathroom with another girl? It's like they gotta be with another girl or they have to have a boyfriend. It's like they either have a boyfriend or they're with a girlfriend. It's like they can never what? Be alone. That's a diatomic element, and it's unstable when they're alone. Right? Now, in the real world, it's not good that they are so dependent. But here, oxygen has to be O2. Or, look at my scenario. Who was I earlier? Water. I was water, right? Now, in my picture of water, it did say H2O, but it's really not H2 together, is it? Are the two H's together? This is when I wish I had like letters to hold, so you ought to see this, okay? Are the H's together here? This is H, this is H. Are the H's together? Who's the H bonded to? O. So really, could I call it HOH? That's a more descriptive way to say it, isn't it? In my scenario, I have H and I have O. They're supposed to be diatomic, but they're not diatomic here. Why not? Because they are diatomic when they are alone, or they have to be what? Bonded to something else. Are we bonded? Yes. Why is it more stable to be H2 or O2 or F2 or Br2? Why is it more stable? You can get this very easily. Here's H. Here's H. Actually, let me say, here's H, here's H, here's the one electron, here's the one electron, okay? What do I make when I put H with H? A single bond. And do I make H2? Now, do I have two electrons being shared? Now, this is going to go on into some later stuff that we're going to do next Monday probably, maybe Wednesday. Here is that perfect sharing relationship. I said it hardly ever existed, didn't I? This is it right here. Because this hydrogen has an electronegativity of whatever it is, 2.20. This hydrogen has an electronegativity of 2.20. So what are they saying about these electrons? You get it 5 minutes, I get it 5 minutes. You get it 5 minutes, I get it 5 minutes. And they're happy. They're perfect. This is perfect sharing right here. Hydrogen, H2. This is perfect sharing. O2. Also, perfect sharing. F2, perfect sharing. You follow what's going on? So are they more stable? Very stable. In fact, think about it for a minute. If you remember my goofy scenario at the end of class, I think Monday, when I was like, sodium's walking down the street and chlorine, that was a bunch of baloney. Obviously. Okay. Oh, maybe it wasn't baloney to you all. Okay, sodium could walk down the street by itself because sodium can exist alone in nature, right? But what about chlorine? You know what? It's chlorine with its other little chlorine friend. You follow me? So you got chlorine and chlorine. So chlorine and chlorine are walking down the street and they're single sodium and they're saying, he's really cute, isn't he? Yeah, he is. He's really cute. I want him. No, I want him. What has to happen for them to break this bond up? You got to have another sodium. Think about it. Chlorine has how many valence electrons? 7. Now, some of you are not being able to go from this sharing chlorine scenario to that ion scenario I'm talking about. Let me show you. Picture, again, this is corny, but picture 2 electrons up here. I'm chlorine right now. 2 electrons. How many am I? 2, 4. Actually, let me do it this way. 2, 4, 6, 7, 1. Does that make sense? 2, 4, 6, 7. Yes? And I've got another one over here. 2, 4, 6, 7. You with me? Now you get my picture up here I'm trying to draw? So chlorine with its 7. Chlorine with its 7. What do these two do? Share. So we're hooked together now, right? Cl2, yes? And then over here we have sodium with its 1. And we have 1 sodium with its 1. You follow? Guys, what I'm explaining to you right now is chemical reactions. This sodium with its 1 reacts with Cl2, but how does it break up Cl2? Can 1 Na break up Cl2? No. You have to say, Na says, brother, come with me, and we're going to go break them up. So it takes 2 NAs to break up Cl2, then you get 2 NaCls. Does that make sense at all? Some of you are getting it, and you're starting to see the big picture. So here, when we're Cl2, we're molecular. This is a molecule called a diatomic molecule. And in a minute, we're going to draw these pictures that I'm trying to show you on paper. Then we take this Cl2 molecule, react it with sodium atom, and that sodium atom loses an electron, gives it to the Cl so that the Cl now is happy and sodium's happy and they're NaCl, but in order to break that up, it had to have another Na to do that. Is that, you follow? Some of you are shaking your head, yes, good. Okay, so how are we going to represent all of this? We're going to represent it with Lewis structures. Lewis structures use dots or dashes for electrons around the symbols of the atoms to show how electrons are being shared or bonded, and the whole goal for everybody is an octet. I've said that 10 times, I think, already. Except hydrogen only needs... Hydrogen needs a total of 2. Hydrogen only needs 2. Why? First energy level can only hold how many? That's right. First energy level holds 2 because it only has an S. That's why. So the first energy level holds 2. So I'm going to show you how electrons can bond. Let me get your heads wrapped around where we are. We're leaving for a little while ionic compounds, and we're going to sharing electrons, meaning covalent or molecular compounds. If I call them covalent, I mean molecular. If I call it molecular, I mean covalent. Bottom line, I mean sharing electrons. That's what we're talking about. So we're looking at sharing electrons. You can share them in a single bond. You can share them in a double bond. You can share them in a triple bond. That's the 3 ways you can share electrons. Single, double, or triple. There are no Jameses here. You don't get that, do you? All right. I'm trying. Wake you up. All right. Single bond would be how many electrons do you think? Total. 2. This is a single bond. 2 electrons. Double. 4. Triple. 6. Now, James would be as many as he can get. But we're only doing single, double, and triple. So single bond is 2 electrons. Double bond is 4 electrons. Triple bond is 6 electrons. If we use dots to show these electrons, which is what I've been up here doing in a sense, you're looking at 2 dots, 4 dots, 6 dots. Typically, though, with our bonds, we will not use dots, we will use dashes. So we will always use dashes for bonds. And that's 1 dash, 2, or 3. We will use dashes for bonds. The only time we will use dots, you will use dots for unbonded electron pairs called lone pairs. Those are called lone pairs. What's the goal again for everyone except hydrogen? 8. What's the maximum that can be shared based on what I'm showing you here? 6. What does that mean? That means you can't share everything. Do you follow what I'm saying? You can share up to 6 electrons between 2 atoms. So if I have an atom here and I'm an atom, I can share a maximum of 6 electrons, but can I share all 8? No. You have to have some of your own. You cannot share them all. You have to have some of your own. This bottom half of this page deals with the rules for sharing electrons. We're going to get here tonight, but right now I'm not going to start here. I'm going to flip to the next page, and we're actually going to do the Lewis structures for the diatomic elements, because I've pretty much already done some of these for you. And I want us to confirm the look of these, then we'll come back to the rules, okay? First, who are the diatomic elements? Hofbrinkel. So what we are going to do is we are going to draw the Lewis structures for the diatomic elements. Lewis structures use symbols and dashes to show how these are put together. In other words, somebody standing up here looking dumb is no longer needed. Now we can do it on the paper. And we can put atom symbol, a dash, atom symbol, dash, and show what we're doing. So let's do the Lewis structure for H2. Now the first thing I'm going to do is actually show this to you with colors, and I'm going to zoom in a little bit and see if that helps you. I'm going to show this to you with colors. There's H with its 1 valence electron. Here's H with its 1 valence electron. What are they doing? Sharing. Now, I already told you today I don't want you using dots for bonds, so a better way to write this is simply that. That is the Lewis structure for hydrogen. That's it. H2, H-H. That's me standing up with my fingers locked. That's what I'm doing. Does that make sense? Why do we not need an octet? Because hydrogen only needs 2. So we just took care of hydrogen. I'm going to skip oxygen and I'm going to go to fluorine. F2. And I'm going to do the same thing. I'm going to use colors. You don't have to use the colors. I'm just showing you. If some of you need this visual, these are the 7 valence electrons for fluorine. These are the 7 valence electrons for this fluorine. They put their 2 singles together, which makes them have a what kind of bond? Single bond. Then if I cover one of these up, how many does that left hydrogen have, or fluorine have rather? 8. How many does the right fluorine have? 8. Are they both happy? Yes. So the better way to write it is F dash F, and that, the lone pairs rather, go around those. That's what a lone pair is. So there are 6 lone pairs, 1, 2, 3, 4, 5, 6 lone pairs around the fluorine. Now you tell me who else looks like fluorine. Who else looks like fluorine? Chlorine. Why? Same column. Who else? Bromine. Who else? Now, some of you are like, where's she getting valence electrons from? Where did she get 7 dots to begin with? Valence electrons. First column, how many valence electrons? 1. Second column, how many valence electrons? 2. Third column, how many valence electrons? With me? Now we got it? So does it make sense that F2, Cl2, Br2, I2 are all going to look the same? So I don't need to do them. They're all done. Now, before I do O2 and N2, I'm actually going to go back to my rules. And I'm going to be quiet. You read the rules. I'm going to quit talking. You read the rules. I'm not going to read them to you. Read the rules real quickly. Now let's follow the rules while we do O2. Count the total number of valence electrons. If it is an anion, you'll add. If it's a cation, you'll subtract. O2 is not an anion or a cation. So count the total number of valence electrons. That's 2 atoms. That's the number of atoms times 6 valence electrons. That's a total of how many? 12 electrons. VE is valence electrons. VE. So 2 atoms times 6 valence electrons, that's 12 total electrons. That's step 1. Step 2, determine the central atom, usually the one you have the fewest of, and usually the atom that is the least electronegative. Well, guys, we only have 2 atoms. There's not going to be a central atom. So keep reading. What's it say? Connect together. With what kind of bond? Single bond. So just simply put O-O. 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 And now we have to do our accounting. It says count the number of electrons used to form the single bond and subtract that from the total. How many did we just use? 2. You just used 2. So you have to take that away from the total. You've already used them. So 2 electrons used, that means you have 10 left over. Keep reading. Use the remaining electrons to place in pairs around all atoms. It says place them around the most electronegative atom first. They're both the same. You just put all of them on one, then go to the next. Do not even them up. You have to keep them in pairs. Don't even them up. So we're simply going to go 2, 4, 6, 8, 10. So now have we used all the electrons that we have? Yes. All right. Are we done? No, we are not done. You're doing like this. You don't know if you're done or not. No, we're not done. Why are we not done? Look at this oxygen. Happy or sad? It's happy. Sad. Why is it sad? It doesn't have 8. So keep reading. If there are not enough electrons to give each atom an octet, rearrange the pairs of electrons to form double or triple bonds as needed. Now, how do you know where to do that or how to do it? Electron pairs are taken from the atom that has the most and placed between that atom and the needy atom. In doing this, the atom that had them to begin with doesn't lose them. It's sharing them. So pick 2. I don't care which 2 you pick. Just pick a pair. I'm going to pick that pair, and I'm going to put them in the middle. And then when I do that, it becomes O double bond O. And that is the Lewis structure. How do I know I'm right? I count. Does each atom have 8? Then I also count 2, 4, 6, 8, 10, 12. Is that how many I should have to begin with? Yes. Now you do N2. You do N2. Do you get 14 electrons total? Do you see that? That's not right. I hope you don't see it. You better be saying no. No. Tell me. It's wrong. It's wrong. What should it be? 2 times 5. Good. Wake up. 10 electrons total. That's what you should get. 10 electrons total. Yes, now? All right, wake up there. So now what? Guys, you got a few minutes. Wake up till you get home. Come on. What's going on? What do we do first? Single bond. And what do? Subtract those 2. How many does that leave us? 8. Place them in pairs. Give all of them to one person, then move to the other. Don't split them up 4 and 4. So you go 2, 4, 6, 8. Now, rearrange those and make everybody happy. And tell me what you come up with. It has to be in with the triple bond. That's exactly right. Chances are, first, you actually just made the double. And then you put those in the middle, and then you said that N still not happy. So it actually takes a triple. So N, triple bond, N. And that is your final Lewis structure. Real quick, draw water. You've seen me be water today. Real quick, follow the rules and draw water. Even if you don't have to follow the rules, just draw water if you can do it without following the rules. Draw water. Draw the Lewis structure for water. I'm going to do it by the rules just so that you have it down. Does that make sense? What did I do? I said 2 atoms of hydrogen times what? Each has what? 1 valence electrons plus 1 O. It has 6 valence electrons. That made a total of how many? 8 electrons. Can hydrogen be a central atom? No, because it only needs how many? 2. So it had to be oxygen. And then it said bond the atoms together, placing your central atom, and then bond everybody to the central atom with single bonds. Now, I tend to do things in a straight line. You could have done it differently. It didn't matter. You could have put H up here or down here. I did it in a straight line. Where did the -4 come from? The 2 single bonds I used, and then what did these 4 do? Top and bottom. Does it make sense? Go ahead. You put them in pairs around who needs them. And hydrogen doesn't need them, because hydrogen only needs 2 and it has them. Okay? Guys, try a couple more of these and watch the videos, and I will see you on Wednesday.